3.2 billion light-years away, two different telescopes just measured the speed of the universe expanding. They did it with the most precise instruments humanity has ever built. Data from the James Webb Space Telescope, observations from the Hubble Space Telescope, and cosmic radiation measurements mapped by the Planck Space Observatory. The numbers should match. They don't. One method says the universe expands at roughly 67 kilometers per second per megaparsec. Another insists the true number is closer to 73. Both measurements are extraordinarily precise. Both come from decades of data. Both have passed every calibration test scientists could throw at them, and yet they disagree, not by a tiny margin that might vanish with better measurements. By nearly 9%. In cosmology, that gap is enormous. It means something in our understanding of the universe might be wrong. And the deeper scientists looked, the stranger the problem became, because the conflict does not appear in rough estimates or preliminary observations. It shows up in the most refined measurements modern astronomy can produce. Independent teams, different telescopes, different methods, all converging on two answers that refuse to reconcile. The data held, which left researchers with an unsettling possibility. The model that describes how the universe works, the framework that explains galaxies, dark matter, and the origin of cosmic structure, might be missing something fundamental. But before we dive into equations, telescopes, and cosmic radiation, it helps to imagine the problem in a way that feels closer to everyday life. Picture a vast lake at sunrise. You toss a stone into the water and watch ripples spread outward in perfect circles. The farther the ripple travels, the slower it should move as its energy fades. The pattern is simple, predictable, something you could measure with a ruler and stopwatch. Now imagine two scientists standing on opposite sides of that lake measuring those ripples. One calculates the waves slowing exactly as physics predicts. The other measures the same ripples and finds them moving noticeably faster. They check their rulers. They check their clocks. They repeat the experiment again and again. The lake is calm. The measurements are precise. And yet the numbers refuse to agree. Something about the system is behaving differently than expected. That is essentially what cosmologists are seeing when they measure the expansion of the universe. Because space itself is stretching, not like an explosion throwing galaxies outward through empty space, but more like the fabric between galaxies slowly expanding, carrying everything with it. The discovery that this was happening came nearly a century ago. In the late 1920s, astronomer Edwin Hubble made a simple but revolutionary observation using the Mount Wilson Observatory. Distant galaxies were moving away from us, and the farther away they were, the faster they appeared to recede. The relationship was strikingly clean. Distance on one axis, speed on the other. Draw the points on a graph, and they line up almost perfectly. This relationship became known as Hubble's law. At its heart lies a single number, the Hubble Constant. It tells us how quickly the universe expands. Measure that number precisely, and you can estimate the age of the universe, reconstruct its past, and predict its ultimate fate. For decades, astronomers refined that measurement. Better telescopes, better detectors, better distance measurements to faraway galaxies. By the early 2000s, the value appeared to be settling into place. Then something unexpected happened. Two different techniques began producing two different answers. One method looked at nearby galaxies using Cepheid variable stars and type Ia supernovae. The other method looked deep into the early universe using the cosmic microwave background. Each technique was independently precise. Each passed rigorous statistical tests, and each pointed toward a different cosmic expansion rate. At first, researchers assumed the discrepancy would disappear. Maybe one telescope needed recalibration. Maybe one dataset contained hidden systematic errors. So scientists did what scientists always do. They checked everything, again and again and again, but the numbers refused to budge. The disagreement remained, and slowly, quietly, a phrase began circulating through cosmology departments around the world. The Hubble Tension, a small-sounding name for a problem that might force physicists to rethink how the universe actually works. Because if both measurements are correct, then the universe itself might be behaving in a way no existing theory predicted. And the most unsettling discovery was still buried deeper in the data. For a long time, most cosmologists believed the disagreement would vanish. Science is full of small discrepancies that disappear as measurements improve. A telescope gets upgraded, a dataset grows larger, a hidden calibration error is discovered. The numbers slowly converge. That is the normal story. The Hubble tension refused to follow it. Instead of shrinking, the gap began to look more solid. To understand why that alarmed scientists so deeply, we need to talk about what the Hubble constant actually represents. Imagine the universe as a gigantic loaf of raisin bread slowly baking in the oven. As the dough expands, every raisin moves away from every other raisin. The farther apart two raisins start, the faster the distance between them grows as the dough stretches. No raisin sits at the center of the expansion. The dough itself is expanding everywhere at once. Galaxies behave exactly like those raisins. Space itself stretches between them. The Hubble constant simply tells us how quickly that cosmic dough is expanding right now. If the number is larger, the universe expands faster. If the number is smaller, expansion is slower. That difference might sound subtle, but it carries enormous consequences. A faster expansion rate implies a younger universe. A slower rate implies an older one. Even more important, the expansion rate encodes the entire history of cosmic evolution, how matter clumped into galaxies, how dark energy accelerated expansion, how the large-scale structure of the universe formed. So when two measurements disagree about the Hubble constant, they are not just disagreeing about a number, they are disagreeing about the story of the universe itself. The first measurement method looks at relatively nearby galaxies. Astronomers measure distances using a cosmic ladder built from objects whose brightness is predictable. The ladder begins with stars close enough for geometric measurement, then climbs outward using increasingly powerful indicators. One of the most important steps involves Cepheid variable stars. These stars pulse rhythmically, brightening and dimming over regular intervals. The length of their pulsation cycle tells astronomers their true brightness. Compare that intrinsic brightness to how bright they appear from Earth, and you can determine their distance. Cepheids act like cosmic mile markers. Once scientists measure distances to galaxies hosting Cepheids, they look for another phenomenon, type Ia supernovae. These stellar explosions reach nearly identical peak brightness. They are visible across enormous cosmic distances and serve as standard candles. By calibrating supernova distances with Cepheids, astronomers can measure how quickly distant galaxies are receding. When this entire system is applied carefully, it produces a value for the Hubble constant around 73 kilometers per second per megaparsec. That means for every 3.26 million light-years of distance, galaxies appear to move away about 73 kilometers per second faster. The farther you look, the faster galaxies recede. The measurement is elegant and direct, but the second method is even more remarkable. Instead of looking at nearby galaxies, it looks back almost 14 billion years to the earliest light in the universe. That light is called the cosmic microwave background. Roughly 380,000 years after the Big Bang, the universe cooled enough for atoms to form. Before that moment, the cosmos was a glowing plasma where photons scattered constantly. Once atoms formed, light could travel freely for the first time. Those photons are still traveling today. Over billions of years, the expansion of space stretched their wavelengths until they became microwave radiation, a faint glow filling the entire universe. Satellites like the Planck Space Observatory mapped this radiation in exquisite detail. The tiny fluctuations in that cosmic glow reveal the exact density of matter, dark matter, and radiation in the early universe. From those patterns, cosmologists can reconstruct how the universe should expand over time, and when they run those calculations forward to today, they obtain a Hubble constant of about 67 kilometers per second per megaparsec, not 73, 67. At first glance, the difference seems small, but cosmology is a field built on precision. The uncertainty in each measurement is only about 1 to 2%. The discrepancy is roughly 9%. That means the two values disagree by several standard deviations far beyond what random error should produce. Scientists sometimes refer to this situation using a phrase borrowed from particle physics, a 5 sigma problem, meaning the odds of the discrepancy appearing by chance are less than 1 in a million. The first reaction was caution. Researchers assumed something must be wrong with the observations. Maybe Cepheid stars behaved slightly differently than expected. Maybe supernova brightness varied subtly across galaxies. Maybe the cosmic microwave background calculations relied on assumptions that needed adjustment. Teams around the world began re-examining the data. They recalibrated detectors. They reanalyzed archived observations. They compared independent surveys. And they launched new instruments designed specifically to test the discrepancy. One of those instruments was the James Webb Space Telescope. Webb's infrared sensitivity allows it to measure Cepheid variables more precisely than any telescope before it. If errors in earlier observations were responsible for the tension, Webb should reveal them. Astronomers pointed Webb toward galaxies that had already been studied with the Hubble Space Telescope. They measured the same Cepheids again, with sharper images, better detectors, less interference from dust. The expectation was simple. Either Webb would confirm the earlier measurements, or it would reveal hidden errors and bring the expansion rate closer to the lower Planck value. The data came back. Scientists ran calibration checks. They reprocessed the images. They compared Webb measurements with Hubble's older data. Everything lined up. The Cepheid measurements were correct. If anything, Webb's data made the tension worse. The local universe still pointed firmly toward a faster expansion rate, which meant the problem was no longer easily dismissed as observational error. Something deeper was happening, and the next possibility was far more unsettling, because if the measurements are both correct, then the theory that connects them, the standard model of cosmology, might be incomplete. For most of the last 20 years, cosmology has operated under a remarkably successful framework. It is known as the LCDM model, short for lambda cold dark matter. The name sounds technical, but the idea behind it is surprisingly simple. The universe contains 3 major ingredients: ordinary matter, dark matter, and something called dark energy. Ordinary matter is the part we understand best. It includes atoms, stars, planets, gas clouds, and every visible structure we can observe. But it turns out that this familiar material makes up only about 5% of the cosmos. Roughly 27% consists of dark matter, an invisible substance that does not emit light, but exerts gravitational influence. Without it, galaxies would not hold together. And the remaining 68% appears to be dark energy, a mysterious force that drives the accelerating expansion of the universe. Together, these components form the backbone of the LCDM model, feed them into Einstein's equations of gravity, run the cosmic clock forward, and the simulation reproduces the large-scale structure of the universe astonishingly well. Galaxy clusters appear where they should. Cosmic microwave background patterns match observations. The growth of structure over billions of years follows the same trends astronomers see in surveys. For decades, LCDM seemed almost perfect. Then the Hubble tension appeared, and suddenly, the model faced an uncomfortable question. What if one of its ingredients is wrong? To understand why that possibility is so disruptive, imagine a giant cosmic puzzle. The LCDM model is like the picture printed on the puzzle box. Every observation we make about the universe is a piece that should fit somewhere in that picture. For a long time, almost every piece fit beautifully. Then a new piece arrived, and it didn't fit anywhere. At first, scientists tried rotating it. Maybe the discrepancy came from subtle observational biases. Maybe distance measurements to galaxies were slightly off. Researchers spent years testing those possibilities. They examined the Cepheid variable stars again. They checked whether metallicity, the chemical composition of stars, could influence brightness measurements. They analyzed dust absorption that might dim light from distant objects. None of it solved the problem. Then they examined the early universe measurements. The cosmic microwave background data from the Planck Space Observatory is incredibly precise, but it relies on a theoretical model to interpret the patterns. Perhaps the interpretation was flawed. Scientists recalculated the cosmological parameters using alternative statistical methods. They tested different assumptions about neutrino masses. They varied the density of dark matter. They altered curvature parameters to see if the universe might not be perfectly flat. Again, the results held. The early universe expansion rate remained stubbornly near 67 kilometers per second per megaparsec, and the local universe still insisted on 73. Two answers, both correct within their own frameworks, both incompatible with each other. At that point, researchers began exploring a more radical possibility. Maybe something happened in the early universe that changed the expansion rate over time, something the LCDM model does not include. One idea involves a hypothetical phenomenon called early dark energy. In the standard cosmological picture, dark energy only becomes important billions of years after the Big Bang. But what if a brief burst of dark energy-like behavior occurred much earlier? Imagine the universe as a balloon inflating steadily. Early dark energy would be like a short, sudden push on the balloon during its early expansion. That push could slightly alter the density fluctuations encoded in the cosmic microwave background. And if those fluctuations were different, the predicted expansion rate today might shift closer to the locally measured value. In theory, that could resolve the tension. But the idea introduces new complications. Early dark energy must appear at precisely the right moment in cosmic history. It must have exactly the right strength, and it must vanish quickly enough to avoid disrupting other cosmological observations. Models have been constructed to test the idea. Some show promise, but none have yet provided a fully satisfying solution. Another possibility is even stranger. Perhaps the universe contains additional kinds of particles that interact weakly with normal matter. These hypothetical particles are sometimes called extra-relativistic species. In simpler terms, imagine that the early universe contained a bit more radiation than we currently account for. That additional radiation would subtly influence how matter and energy evolved in the first few 100,000 years after the Big Bang. Those changes could ripple forward through cosmic time and affect the predicted expansion rate. Physicists have proposed candidates for these extra particles. Some models suggest new forms of neutrinos. Others invoke entirely new families of light particles. But every new particle introduced into the model must also satisfy constraints from particle physics experiments. So far, no clear evidence has emerged. Then there is an even more dramatic possibility. Perhaps gravity itself behaves differently on the largest scales. Einstein's theory of general relativity has passed every experimental test we have thrown at it, from the orbit of Mercury to gravitational waves detected by observatories like LIGO Scientific Collaboration. The equations describe gravity with extraordinary accuracy, but those tests mostly occur within galaxies or across relatively small cosmic distances. The Hubble tension raises the possibility that gravity might behave slightly differently across billions of light years. Some theorists have explored models involving a fifth force, an additional fundamental interaction beyond the four known forces of nature. Others investigate modifications to general relativity itself. Tiny adjustments to gravitational equations could, in principle, alter how cosmic expansion evolves. But changing gravity is not a simple fix. General relativity connects to virtually every aspect of astrophysics. Modify it incorrectly, and the entire structure of cosmology collapses. So each new model must survive an enormous battery of observational tests. Many have been proposed. Most fail. A few remain under active investigation. Which brings us to the emotional center of this mystery. Because behind every equation, every telescope observation, and every simulation lies a very human reaction: For years, cosmologists believed they had finally assembled a nearly complete picture of the universe. Not every detail was known, of course. Dark matter and dark energy remained mysterious, but the framework connecting everything together seemed stable. The Hubble tension cracked that stability, quietly at first, then more loudly as evidence accumulated. In conference talks and research seminars, scientists began asking questions that would have seemed almost absurd a decade earlier. What if LCDM is incomplete? What if the early universe behaved differently than we thought? What if some entirely new physics is waiting to be discovered? These questions are not signs of failure. They are signs that science is working exactly as it should. Because the history of physics is full of moments like this. Moments when observations refuse to match theory. Moments when the universe reveals a tiny inconsistency that eventually leads to a deeper understanding of reality. At the beginning of the 20th century, a similar inconsistency appeared in the orbit of Mercury. Newton's equations predicted a slightly different orbit than astronomers observed. For decades, the discrepancy remained unexplained. Then Einstein developed general relativity, and suddenly the puzzle piece fit perfectly. What had looked like a small anomaly turned out to be evidence for a completely new understanding of gravity. Cosmologists today wonder whether the Hubble tension might represent a similar turning point, a small mismatch in numbers that could open the door to a deeper theory of the universe. But before we jump to new physics, there is one more crucial piece of the story, a moment when the data itself forced scientists to stop and look at the problem from an entirely different angle. Because the true magnitude of the tension did not become clear until researchers began comparing not just two measurements, but the entire timeline of the universe. And when they did, the room reportedly went very quiet. To see why the room went quiet, imagine compressing the entire history of the universe into a single calendar year. January 1st begins with the Big Bang. The first stars ignite around mid-February. Galaxies assemble through March and April. Our Milky Way galaxy takes recognizable shape sometime in late spring. The solar system forms in early September. Life appears on Earth a few days later. Dinosaurs dominate around Christmas. Humans arrive just minutes before midnight on December 31st. Now imagine measuring the expansion of the universe using two different snapshots of that cosmic calendar. One measurement comes from the first 380,000 years after the Big Bang, effectively January 1st in our analogy. That snapshot is encoded in the cosmic microwave background. The other measurement comes from galaxies that exist billions of years later, closer to the modern era of the universe. In other words, the two measurements come from opposite ends of cosmic history, the early universe and the present universe. The LCDM model assumes a smooth bridge connecting those two eras. The expansion rate should evolve predictably over time. If we know how the universe behaved early on, we should be able to calculate how it behaves today. But when cosmologists tried to connect those two measurements, something unexpected happened. The bridge didn't line up. The early universe predicted a slower expansion today. The modern universe insisted on a faster one, which left researchers with an unsettling implication. Something might have changed in the expansion history of the universe between those two epochs. Not dramatically, not violently, just enough to shift the cosmic expansion rate by a few percent. But even a few percent matters enormously across billions of years. Think of it like a spacecraft traveling across the solar system. If its trajectory deviates by just 1 degree at launch, the final destination millions of miles away will be completely different. The Hubble tension is like discovering that the universe's trajectory may have shifted slightly somewhere along its journey, and that realization triggered a wave of new investigations. Researchers began examining other cosmic distance indicators to see which side of the tension they supported. One method involved gravitational lensing time delays. When light from a distant quasar passes near a massive galaxy, gravity bends the light and creates multiple images of the same object. Those images arrive at Earth at slightly different times. By measuring the delay between them, astronomers can infer distances and expansion rates. Several teams applied this technique. The result again favored the higher expansion rate, closer to 73. Another method uses giant elliptical galaxies, whose stars move in predictable patterns. By analyzing the motion of those stars and the geometry of gravitational lensing around them, scientists can infer cosmological distances. Those measurements also lean toward the faster expansion rate. Even studies using water megamasers, natural microwave lasers, produced in the disks of supermassive black holes, pointed in the same direction. Different methods, different telescopes, different physics, yet many converged toward the higher value, which made the situation increasingly difficult to ignore. The discrepancy was no longer just a disagreement between two measurements. It was becoming a persistent pattern, and patterns in science demand explanation. One possibility still lingered. Maybe the cosmic microwave background interpretation was subtly wrong. Not the observations themselves. The data from the Planck Space Observatory is among the most precise measurements ever taken in astronomy. But the interpretation of that data depends heavily on the LCDM model. If the model is incomplete, the conclusions drawn from the cosmic microwave background might shift. This idea prompted scientists to examine alternative cosmological models. Some involve new forms of dark matter. Others introduce interactions between dark matter and dark energy. Still others modify how energy behaves in the early universe. Each model attempts to preserve the success of LCDM while resolving the Hubble tension. But there is a problem. The LCDM model fits an enormous range of observations with remarkable precision. Any modification must preserve all of those successes. Change the model too much, and it stops matching the cosmic microwave background patterns, or the distribution of galaxies, or the formation of large-scale structures across billions of light years. It's like adjusting a complex mechanical watch. Move one gear slightly, and several others shift as well. Many proposed solutions solve one problem only to create another. And that brings us to the emotional heart of the tension. Because cosmology is not just about numbers, it's about confidence in the framework that explains our universe. For 2 decades, LCDM has been the backbone of modern cosmology. It tells us the universe is about 13.8 billion years old. It explains why galaxies cluster the way they do. It predicts how cosmic structure grew from tiny fluctuations in the early universe. The model works astonishingly well, except for this one stubborn discrepancy. And sometimes in science, a single anomaly is all it takes. The orbit of Mercury exposed a flaw in Newtonian gravity. The ultraviolet catastrophe led to quantum mechanics. The Michelson-Morley experiment paved the way for Einstein's relativity. Each began as a small inconsistency. Each eventually transformed physics. The Hubble tension may represent a similar moment, a subtle crack that hints at a deeper layer of cosmic physics waiting to be uncovered. But before scientists embrace that possibility, they must confront one final question. A question that forces us to step back and truly grasp the scale of the universe itself. Because the expansion of space is not just a number in an equation. It is a phenomenon unfolding across distances so vast that human intuition struggles to comprehend them. And when you finally feel those distances, when you translate cosmic expansion into something relatable, the mystery becomes even more astonishing. To feel what cosmic expansion really means, you have to abandon the idea that space is mostly empty and still, because it isn't. Space is dynamic. It stretches, and it does so across distances so enormous that numbers alone stop carrying meaning. Let's start small. Light, the fastest thing in the universe, travels about 300,000 kilometers every second. At that speed, it can circle Earth more than 7 times in a single second. It reaches the moon in just over 1 second. The sun is about 150 million kilometers away, which means sunlight takes roughly 8 minutes to reach Earth. Already the distances are staggering, but in cosmic terms, this is still our immediate neighborhood. The nearest star beyond the sun, Proxima Centauri, lies about 4.2 light-years away. Even traveling at the speed of light, the journey takes more than 4 years. At the speed of a commercial airplane flying 600 miles per hour, that same trip would take roughly 7 million years. Now expand your perspective. Our Milky Way galaxy spans about 100,000 light-years from edge to edge. If you could cross it in that same airplane, the journey would take nearly 170 trillion years. That is more than 10,000 times longer than the current age of the universe. And the Milky Way is just one galaxy among hundreds of billions. The nearest large neighbor, the Andromeda Galaxy, sits about 2.5 million light-years away. Beyond that lie clusters of galaxies, then superclusters, then enormous cosmic filaments stretching across hundreds of millions of light-years, and all of it is drifting apart. The expansion of the universe is not something that happens in one place. It happens everywhere, between galaxies, between clusters, across the entire cosmic web, and the farther apart two galaxies are, the faster the space between them expands. This is where the Hubble Constant becomes more intuitive. Imagine placing two galaxies 1 megaparsec apart. A megaparsec is about 3.26 million light-years. If the expansion rate is 73 kilometers per second per megaparsec, then those galaxies drift apart at 73 kilometers per second. Place them twice as far apart 2 megaparsecs, and their separation increases at 146 kilometers per second. 10 megaparsecs apart, now the separation grows at 730 kilometers per second. At distances of billions of light-years, galaxies recede at significant fractions of the speed of light, not because they are moving through space quickly, but because space itself is expanding between them, and this expansion is not slowing down. In fact, it's accelerating. That discovery arrived in 1998, when two independent teams studying Type Ia supernovae made an astonishing observation. Distant galaxies were not just receding, they were receding faster than expected. The expansion of the universe was speeding up. The cause of that acceleration became known as dark energy. We still do not know what dark energy actually is. It might be a property of space itself. It might be a new field permeating the universe. Or it might signal something fundamentally missing in our understanding of gravity. But whatever it is, dark energy dominates the large-scale behavior of the cosmos. Roughly 2/3 of the universe's total energy appears to exist in this mysterious form, and its influence grows stronger over time. As galaxies drift farther apart, gravity between them weakens. Dark energy, however, does not weaken. It continues pushing space outward, which means the expansion of the universe gradually accelerates. This acceleration is built into the LCDM model. It explains why distant supernovae appear dimmer than expected. It matches observations of large-scale cosmic structure, and it fits beautifully with the cosmic microwave background. But the Hubble tension complicates this picture, because if the present-day expansion rate is higher than predicted, then something in the model might be incomplete. Maybe dark energy behaves differently than we assume. Maybe its strength changed at some point in cosmic history. Or maybe another component of the universe influenced expansion in ways we have not yet accounted for. Some researchers have proposed the existence of mirror dark matter, a hidden sector of particles that interact weakly with our familiar universe. Others explore the possibility that dark matter itself might decay slowly over time. Still others investigate whether neutrinos, nearly massless particles that flood the cosmos, might play a larger role in cosmic evolution than previously believed. Each of these possibilities introduces subtle adjustments to the expansion history of the universe, and each must be tested against an enormous body of astronomical observations. Cosmology today resembles a vast detective investigation. Researchers gather clues from telescopes, satellites, and galaxy surveys. They compare measurements taken across billions of light-years and billions of years of cosmic time. They run simulations on supercomputers to see how different models reproduce the observed universe. Most models fail quickly. A few survive longer, but none have yet solved the Hubble tension completely. Which brings us to one of the most fascinating aspects of this mystery. Because while scientists debate equations and models, the universe continues revealing new clues. The most powerful observatories ever built are now peering deeper into cosmic history. The James Webb Space Telescope can observe galaxies forming only a few 100 million years after the Big Bang. The upcoming Vera C. Rubin Observatory will map billions of galaxies and track how cosmic structure evolves over time. Meanwhile, gravitational wave observatories are beginning to detect collisions between neutron stars and black holes across vast distances. Each new observation offers another piece of the puzzle, and slowly, the picture of the universe is becoming richer and more complicated than anyone expected, because the Hubble tension might not simply be a measurement error, it might be a signal, a clue pointing toward new physics beyond the standard model of cosmology. But if that is true, the implications extend far beyond a single number. They reach into the deepest questions about the universe itself, questions about how cosmic structures formed, questions about how galaxies evolve, questions about whether our understanding of the universe's birth and fate is fundamentally correct, and perhaps most intriguingly, questions about life. Because if the expansion history of the universe is different from what we believed, the environments where galaxies form, stars ignite, and planets emerge may also change. The cosmic stage on which life develops could be far more complex than we imagined, and that possibility leads to one of the most profound connections in this entire story, a connection between the expansion of the universe and the conditions that allow life to exist at all. For most of human history, the question of life in the universe seemed almost philosophical. We could barely see beyond our own galaxy, let alone imagine the environments where life might form. But modern astronomy has changed that perspective dramatically. Over the past 3 decades, scientists have discovered more than 5,000 planets orbiting other stars. These worlds range from gas giants larger than Jupiter to rocky planets not much bigger than Earth. Some orbit blisteringly close to their stars. Others drift far out in frozen darkness. Many exist in places astronomers once believed impossible. These discoveries forced scientists to rethink how planetary systems form, but they also revealed something even more important. The ingredients for life appear to be common. Carbon exists everywhere in the universe. Water forms easily from hydrogen and oxygen. Organic molecules appear in interstellar clouds and on comets. Planets capable of hosting oceans and atmospheres are scattered across the galaxy. In other words, the chemical building blocks of life are not rare, they are widespread. But chemistry alone is not enough. Life requires stability. Stars must shine long enough for planets to cool. Galaxies must evolve without constant catastrophic radiation events. The universe must expand at just the right pace to allow structures like galaxies and stars to form. This is where the Hubble tension becomes unexpectedly relevant, because the expansion rate of the universe influences how quickly matter clumps together under gravity. If the universe expands too rapidly, galaxies might never form. Matter would disperse before gravity could pull it together. If expansion is too slow, galaxies might collapse into dense structures dominated by black holes and violent radiation environments. The balance between expansion and gravity creates the cosmic architecture where stars and planets appear. So even a small shift in the expansion rate can ripple through the entire history of the universe. That ripple affects how galaxies form, how stars evolve, and ultimately, how often environments suitable for life emerge. To see how subtle this balance is, imagine the early universe shortly after the Big Bang. At that moment, the cosmos was incredibly hot and dense. Tiny fluctuations in matter density existed regions where slightly more material gathered than elsewhere. These fluctuations were incredibly small. In the cosmic microwave background maps produced by the Planck Space Observatory, the temperature variations are only about 1 part in 100,000. Yet those tiny variations eventually grew into galaxies, clusters, and the enormous cosmic filaments stretching across the universe today. Gravity slowly amplified the denser regions. Over millions and billions of years, matter collapsed into stars and galaxies. But gravity did not work alone. The expansion of space constantly pulled matter apart. The entire cosmic structure we observe today emerged from the delicate balance between those two forces. Change that balance slightly, and the universe evolves differently, which is why cosmologists care so much about the precise value of the Hubble constant, because that number encodes how the universe expanded throughout its entire history. And if the expansion history is wrong even by a small amount, our predictions about cosmic evolution might need revision. For example, the age of the universe depends directly on the expansion rate. The current estimate is about 13.8 billion years. If the expansion rate was slightly higher in the past, the universe might be younger than we think. If it was slower, it might be older. Even a few 100 million years of difference can matter when modeling the formation of the first galaxies and stars. Then there is the question of the universe's future. For decades, astronomers wondered whether gravity might eventually halt cosmic expansion and pull everything back together in a big crunch. But the discovery of dark energy changed that picture. Instead of slowing down, expansion appears to be accelerating. If dark energy remains constant, the universe will continue expanding forever. Galaxies beyond our local group will drift farther and farther away until they disappear beyond the cosmic horizon. Trillions of years in the future, the observable universe may contain only a few nearby galaxies. The rest will have slipped beyond view. But if dark energy evolves over time, if its strength changes, the future of the universe might look very different. Some models predict a scenario called the Big Rip, where expansion eventually becomes so powerful that galaxies, stars, planets, and even atoms are torn apart. Others suggest dark energy could weaken, allowing gravity to slow expansion. Right now, we simply do not know, and the Hubble tension raises the possibility that our understanding of dark energy itself may be incomplete. If the expansion rate today differs from what the early universe predicts, perhaps dark energy behaves differently than we assume. Maybe its influence changed over time. Maybe it interacts with dark matter in ways we have not yet discovered. Or maybe something entirely new, a field, a particle, a force, is shaping cosmic expansion behind the scenes. This uncertainty is not frustrating for cosmologists. It is exhilarating, because anomalies in physics often lead to breakthroughs. When astronomers discovered that galaxies rotated too quickly for their visible mass, they uncovered evidence for dark matter. When measurements of distant supernovae revealed accelerating expansion, they discovered dark energy. Both findings revolutionized cosmology. The Hubble tension might represent the next step in that process. But before scientists claim a new discovery, they must eliminate every possible conventional explanation. That means examining every instrument, every calibration, every dataset. It means building new telescopes and gathering new observations. It means pushing measurements to unprecedented precision, and that process is already underway. Over the next decade, a new generation of observatories will begin measuring cosmic expansion with extraordinary accuracy. The Vera C. Rubin Observatory will track billions of galaxies and map the growth of cosmic structure. The Nancy Grace Roman Space Telescope will measure distances across vast cosmic scales. Meanwhile, gravitational wave detectors are opening a completely new method for measuring the expansion of the universe. When two neutron stars collide, they produce a burst of gravitational waves, ripples in space-time itself. Those waves encode the distance to the collision. If astronomers also detect light from the same event, they can determine the galaxy where the collision occurred. By combining distance and velocity measurements, researchers can estimate the Hubble constant using an entirely different technique. These events are sometimes called standard sirens. Unlike Cepheid stars or supernovae, they rely on the physics of gravity itself. Early measurements using gravitational waves already hint at expansion rates closer to the higher value. But the data remains limited. Over time, as more collisions are detected, the precision will improve, and eventually, the universe itself will reveal whether the Hubble tension reflects measurement error or new physics. Which brings us to the quiet question circulating in cosmology today. What if both measurements are right? What if the early universe really predicts 67, and the modern universe truly measures 73? That possibility would mean the expansion history of the universe changed in a way our current models cannot explain. Something new would be required, a missing ingredient in the cosmic recipe. And if that ingredient exists, discovering it could reshape our understanding of the universe as profoundly as relativity or quantum mechanics once did. What makes the Hubble tension so fascinating is that it sits at the intersection of observation and theory. Astronomers are not just debating numbers. They are confronting the possibility that the universe itself may contain physics we have not yet discovered. And this would not be the first time something like that happened. At the end of the 19th century, physicists believed they had nearly completed their understanding of nature. Classical mechanics explained motion. Electromagnetism explained light and electricity. Thermodynamics described heat and energy. Only a few small anomalies remained. One of those anomalies involved the spectrum of light emitted by hot objects. According to classical physics, heated objects should radiate infinite energy at ultraviolet wavelengths. The prediction was obviously wrong. Physicists called it the ultraviolet catastrophe. The solution arrived when Max Planck introduced a radical idea. Energy might not be continuous. It might come in discrete packets. That idea became the foundation of quantum mechanics. Another anomaly appeared in the orbit of Mercury. The planet's path around the Sun drifted slightly more than Newton's equations predicted. For decades, astronomers searched for explanations. Some proposed an unseen planet inside Mercury's orbit. Others suspected observational errors. The real explanation came from Albert Einstein. His theory of general relativity showed that gravity arises from the curvature of space-time itself. The extra shift in Mercury's orbit suddenly made perfect sense. In both cases, a small discrepancy led to a profound shift in our understanding of the universe. The Hubble tension might represent a similar moment, but cosmology operates on a scale far larger than atomic physics or planetary orbits. The discrepancies appear across billions of light years and billions of years of cosmic history. To resolve them, scientists must test ideas that stretch the limits of modern physics. Some researchers suspect the key may lie in the behavior of dark energy. In the LCDM model, dark energy behaves like a constant property of space. Einstein originally introduced something similar, the cosmological constant, as a mathematical term in his equations. Later, he abandoned it, calling it his greatest mistake. Ironically, modern observations suggest something like the cosmological constant actually exists, but the Hubble tension raises a subtle question. What if dark energy is not perfectly constant? What if its strength evolved over time? A temporary surge of dark energy early in the universe could shift the cosmic expansion history just enough to reconcile the two measurements. This is the essence of the early dark energy hypothesis. In this scenario, dark energy briefly influenced the universe shortly after the Big Bang. Its presence altered the pattern of density fluctuations imprinted in the cosmic microwave background. Later, its influence faded, leaving today's expansion rate slightly higher than standard models predict. Several theoretical models explore this idea. Some involve new scalar fields, hypothetical energy fields permeating space. Others propose interactions between dark energy and dark matter. These models can sometimes reduce the Hubble tension, but none yet solve the problem completely without introducing new inconsistencies elsewhere. Another possibility involves the mysterious particles known as neutrinos. Neutrinos are incredibly abundant. Trillions pass through your body every second without interacting. They have extremely small masses and rarely interact with matter. But in the early universe, neutrinos played a crucial role in shaping cosmic evolution. If neutrinos behave slightly differently than expected, perhaps possessing additional varieties beyond the three known types, they could alter the expansion history of the universe. Physicists call these hypothetical particles sterile neutrinos. Unlike ordinary neutrinos, sterile neutrinos would interact only through gravity. If they exist, they might influence cosmic expansion during the universe's first few 100,000 years. Experiments on Earth have searched for sterile neutrinos for decades. Some results hint at their existence. Others find no evidence. The debate continues. Then there is the possibility that dark matter itself behaves differently than we assume. In the standard model, dark matter is cold and stable. Cold means its particles move slowly relative to the speed of light. Stable means they persist unchanged over billions of years. But if dark matter decays slowly or interacts weakly with dark energy, the expansion rate of the universe might shift slightly over time. Some models even suggest dark matter might come in multiple varieties with complex interactions. Each new possibility opens a door to unexplored physics. But cosmologists must tread carefully. The LCDM model succeeds at explaining an enormous range of observations. Any modification must preserve those successes while solving the Hubble tension, and that requirement is extremely difficult to satisfy. Which brings us to one of the most intriguing developments in modern cosmology, because new methods for measuring the expansion of the universe are emerging, methods that rely not on stars or galaxies, but on the very fabric of space-time itself. These measurements come from gravitational waves, ripples in space-time produced by violent cosmic events. When massive objects like neutron stars collide, they generate gravitational waves that travel across the universe. Observatories such as LIGO Scientific Collaboration and Virgo Collaboration can detect these waves as they pass through Earth. The waves carry precise information about the distance to the collision. If astronomers also observe light from the same event, they can determine how fast the host galaxy is moving away from us. Distance and velocity together provide a direct measurement of the Hubble Constant. This method bypasses many uncertainties associated with traditional distance ladders. The first gravitational wave measurement of cosmic expansion occurred in 2017 when two neutron stars collided in a galaxy about 130 million light-years away. The event was detected by LIGO and Virgo, and telescopes around the world observed the explosion of light that followed. From that single event, astronomers estimated the Hubble constant. The uncertainty was large. The measurement ranged between about 60 and 80 kilometers per second per megaparsec. But the technique worked. As more gravitational wave events are detected, the precision will improve. Within the next decade, this method could become one of the most powerful tools for measuring cosmic expansion, and it may help determine whether the Hubble tension represents a real physical phenomenon or simply an artifact of measurement. Yet even as scientists pursue these solutions, a deeper philosophical realization is beginning to emerge. The universe may be more complicated than our current models allow, not just slightly more complicated, fundamentally richer, which leads to a question cosmologists rarely ask publicly, but discuss frequently in private. What if the universe still holds entire layers of physics we have not yet discovered? What if dark matter and dark energy are only the beginning? What if the Hubble tension is the first glimpse of something far more profound? The idea that hidden layers of physics might exist in the universe is not as radical as it sounds. In fact, history suggests it may be inevitable. Every time humanity has believed it understood the fundamental workings of nature, new observations have revealed deeper structures underneath. Atoms once seemed indivisible. Then scientists discovered electrons, protons, and neutrons. Later they uncovered quarks and the strange quantum fields underlying them. Gravity once appeared as a simple force, pulling objects together. Einstein showed it was the curvature of space-time itself. Even empty space turned out not to be empty at all, but filled with fluctuating quantum energy. Each discovery expanded our understanding of reality. Cosmology today stands in a similar position. We know the universe contains ordinary matter, and dark energy, but we do not yet understand what two of those components actually are. Dark matter has never been detected directly. Dark energy remains a complete mystery. Together they make up about 95% of the universe, which means most of the cosmos is still unexplained. The Hubble tension sits precisely in the middle of that mystery, because the discrepancy in the expansion rate might be telling us something fundamental about those unseen components. Consider dark matter. Astronomers know it exists because galaxies rotate too quickly for their visible mass alone to hold them together. Clusters of galaxies also reveal its presence through gravitational lensing, the bending of light by invisible mass. Yet no experiment on Earth has successfully detected a dark matter particle. Researchers have built ultra-sensitive detectors buried deep underground to shield them from cosmic radiation. Some experiments use vats of liquid xenon. Others rely on cryogenic crystals cooled close to absolute zero. All are searching for faint signals produced when dark matter particles interact with ordinary matter. So far, the results remain inconclusive. Dark energy is even more mysterious. Unlike dark matter, which behaves like a form of invisible mass, dark energy appears to act as a kind of pressure embedded in space itself. It pushes the universe outward. The strange part is that its density does not dilute as the universe expands. Ordinary matter becomes more spread out over time. Dark energy does not. That property is what allows it to dominate cosmic expansion billions of years after the Big Bang. Yet we do not know why it exists. One possibility is that dark energy arises from quantum fluctuations in empty space. Quantum physics predicts that even vacuum contains energy. But when physicists calculate the expected magnitude of that energy, the result is wildly different from what cosmological observations show. The discrepancy is enormous, more than 100 orders of magnitude. It is sometimes described as the worst theoretical prediction in the history of physics, and the Hubble tension might hint that our assumptions about dark energy are incomplete. Maybe dark energy changes over time. Maybe it interacts with other cosmic components. Or maybe it represents a deeper phenomenon we have not yet recognized. Some physicists have proposed the existence of entirely new sectors of reality-hidden fields or particles that interact only weakly with the visible universe. These ideas sound speculative, but many theories of fundamental physics already predict additional structures beyond the particles we know. For example, certain extensions of the standard model of particle physics predict new light particles that could influence cosmic expansion. Other theories suggest that space-time itself might possess additional dimensions beyond the three spatial dimensions we experience. If gravity can leak into those extra dimensions, its behavior on the largest cosmic scales might change. Such ideas remain speculative, but cosmologists are exploring them seriously because the Hubble tension refuses to disappear. And sometimes in science, persistent anomalies signal the edge of a deeper truth. Yet, before embracing new physics, scientists must examine one final possibility. What if the tension arises not from unknown particles or forces, but from something about the universe itself that we have misunderstood? Because the universe is not perfectly uniform. On the largest scales, matter forms a vast cosmic web. Galaxies cluster along filaments, stretching hundreds of millions of light years. Between those filaments lie enormous cosmic voids regions containing very few galaxies. Our own Milky Way sits within a modestly dense region known as the local group, surrounded by larger structures such as the Virgo supercluster. Some researchers have wondered whether our location in the universe might influence measurements of cosmic expansion. If we happen to live in a slightly under-dense region, a cosmic void nearby galaxies might appear to recede faster than average. That effect could bias measurements of the Hubble constant derived from nearby observations. This idea is sometimes called the local void hypothesis. Simulations suggest such effects are possible, but the magnitude required to explain the Hubble tension appears larger than observations of galaxy distributions allow. In other words, the universe around us does not seem empty enough to produce the discrepancy. Still, scientists continue investigating every possible explanation, because extraordinary claims require extraordinary evidence. Before rewriting cosmology, researchers must be absolutely certain the tension is real, which is why the coming decade may prove decisive. New surveys will measure millions of galaxies across enormous cosmic volumes. Improved observations of supernovae will refine the distance ladder. Gravitational wave detections will provide independent expansion measurements. Meanwhile, the James Webb Space Telescope continues pushing observations deeper into cosmic history. Webb has already revealed galaxies forming earlier than many models predicted. Some appear surprisingly massive for such young cosmic ages. Those discoveries are still being analyzed, but they hint that our understanding of early galaxy formation might also need revision. If the universe formed structures earlier or faster than expected, that could influence cosmological parameters derived from early universe observations. In other words, multiple puzzles may be connected. Cosmology today resembles a detective story unfolding across billions of light years. Every new observation provides another clue. Sometimes the clues reinforce existing theories. Sometimes they reveal cracks in the foundation, and occasionally they point toward entirely new ideas. The Hubble tension may ultimately turn out to be a statistical coincidence. It might disappear as new data accumulates. But many cosmologists suspect something deeper is happening, because the discrepancy has survived years of increasingly precise measurements. It has been tested from multiple angles, and it refuses to go away, which brings us to the quiet realization spreading through the cosmology community. The universe might not be as simple as our current models suggest, not just slightly more complex, fundamentally richer. And if that is true, the Hubble tension might be the first sign that an entirely new chapter in cosmology is beginning. One of the most intriguing things about the Hubble tension is how quietly it emerged. There was no dramatic press conference announcing a crisis in cosmology, no sudden discovery that overturned decades of research overnight. Instead, the problem appeared gradually. A few papers here, a slightly different measurement there, a handful of astronomers comparing numbers and noticing something strange. At first, the discrepancy looked small enough to ignore. Cosmological measurements always carry uncertainties. Astronomers expected that as telescopes improved and datasets expanded, the numbers would slowly converge. But they didn't. The more precise the measurements became, the clearer the disagreement looked. That was the moment researchers began to realize the tension might be telling them something real. And the moment they started asking a deeper question: what if the universe expanded differently at different stages of its history? Because the universe has not always looked the way it does today. Shortly after the Big Bang, the cosmos was an extremely dense plasma of particles and radiation. Protons, electrons, and photons scattered constantly. Light could not travel freely. Instead, it bounced endlessly through a glowing fog of charged particles. During that time, sound waves actually rippled through the plasma, not sound as we hear it on Earth, but pressure waves moving through the hot cosmic fluid. Those waves left imprints in the density of matter. When the universe cooled enough for atoms to form, the plasma cleared. Light escaped. The pressure waves froze into place as tiny variations in matter density. Those variations became the seeds from which galaxies eventually formed. Today we observe the fossil imprint of those ancient waves in the cosmic microwave background, but we also see them in the distribution of galaxies across the universe. Astronomers call these patterns baryon acoustic oscillations. They act as a kind of cosmic ruler. Because the size of the sound waves in the early universe is known, scientists can use that scale to measure distances across billions of light years. By comparing the apparent size of those patterns at different cosmic epochs, astronomers can reconstruct how the expansion rate of the universe evolved over time. And when they do that, something fascinating emerges. For most of cosmic history, the expansion rate behaves exactly as the LCDM model predicts. But when researchers extrapolate those measurements to the present day, the value again lands closer to 67 kilometers per second per megaparsec. The lower value. That means the tension appears strongest only when we compare early universe measurements with very local observations. Something about the nearby universe seems to produce a faster expansion rate than expected, and this brings us to one of the most subtle aspects of the problem. Because measuring distances in astronomy is incredibly difficult. You cannot stretch a measuring tape across millions of light years. Instead, astronomers rely on chains of indirect methods. This chain is known as the cosmic distance ladder. Each step calibrates the next. First come nearby stars, whose distances can be measured using geometric parallax. As Earth orbits the Sun, nearby stars appear to shift slightly against the background of distant ones. That tiny shift allows astronomers to calculate their distance directly. The European space mission Gaia Space Observatory has measured the distances to more than 1 billion stars using this technique. Once astronomers know the distances to certain stars, they can calibrate other distance indicators like Cepheid variables. Those Cepheids then calibrate supernova distances. Supernovae allow astronomers to measure distances to galaxies billions of light years away. Each step depends on the accuracy of the previous one, which means any hidden error could propagate through the entire ladder. For years, critics of the Hubble tension suspected that something in this ladder might be slightly off, but the ladder has now been tested repeatedly. Different teams use different calibration methods. Some use Cepheids, others use a class of stars called tip-of-the-red giant branch stars. These stars reach a predictable brightness just before helium ignition in their cores. That brightness provides another reliable distance indicator, and measurements using this method still produce a relatively high expansion rate, not exactly identical to the Cepheid measurements, but closer to them than to the cosmic microwave background value, which makes the situation even more intriguing. Because the discrepancy persists across different techniques, each method has different systematic uncertainties, yet they still produce similar results. This persistence has slowly shifted the attitude of many cosmologists. What began as skepticism is turning into cautious curiosity. Maybe the tension really is telling us something new, and if it is, the implications extend far beyond a single number. Because the Hubble constant connects almost every aspect of cosmology. It influences estimates of the universe's age. It affects how dark matter shaped galaxy formation. It determines how quickly cosmic structures emerged. And it even influences predictions about the ultimate fate of the universe. A change of just a few % in that number can ripple through the entire framework of cosmology. Which means solving the Hubble tension is not just about fixing a measurement. It may require rewriting part of the story of the universe, and the next clue may come from an unexpected place. Not from galaxies, not from supernovae, but from the faint ripples of space-time itself, because the universe has begun revealing its secrets through gravitational waves, and those waves may soon provide one of the most direct measurements of cosmic expansion ever attempted. On the 17th of August 2017, detectors in the United States and Europe felt something extraordinary pass through Earth. Not light, not particles, but a ripple in space-time itself. 2 neutron stars, incredibly dense remnants of exploded stars, had collided in a galaxy about 130 million light-years away. The collision released a burst of gravitational waves that traveled across the universe before reaching Earth. The signal was detected by instruments belonging to the LIGO Scientific Collaboration and the Virgo Collaboration. For the first time in history, humanity observed both gravitational waves and light from the same cosmic event. The moment changed astronomy, but it also created an entirely new way to measure the expansion of the universe, because gravitational waves carry something incredibly valuable: distance. When 2 neutron stars spiral toward each other, the strength and shape of the gravitational wave signal encode how far away the event occurred. It's like hearing thunder during a storm. The louder the thunder, the closer the lightning strike. But gravitational waves are even better. Their physics is well understood, and the signal strength provides a direct measurement of distance without relying on the cosmic distance ladder. Astronomers call these events standard sirens. The gravitational waves reveal the distance. The light from the explosion identifies the galaxy where the event occurred. From that galaxy, astronomers measure how fast it is moving away due to cosmic expansion. Distance and velocity together reveal the Hubble constant. The first measurement from the 2017 neutron star collision produced a wide range of possible values. The data suggested an expansion rate somewhere between roughly 60 and 80 kilometers per second per megaparsec. That uncertainty was large, but the method worked, and as more gravitational wave events are detected, the uncertainty will shrink dramatically. Within the next decade, astronomers expect dozens, perhaps hundreds of these events. Each will refine the measurement of cosmic expansion. Eventually, gravitational waves may provide the most reliable answer to the Hubble tension, and they do so in a way that bypasses many of the uncertainties affecting traditional methods. This is why cosmologists are watching gravitational wave astronomy so closely, because it may finally reveal which measurement is correct, or something even more surprising, the possibility that both are. If the gravitational wave measurements land closer to 73, the faster expansion rate will gain stronger support. If they settle near 67, the early universe prediction will appear more reliable. But there is also a third possibility. The value could fall somewhere in between. If that happens, the tension might partially dissolve, or it could reveal that the universe's expansion rate actually changes in subtle ways over time. And that possibility leads to a deeper realization, because the Hubble constant might not be constant at all. In the LCDM model, the term Hubble constant describes the present expansion rate of the universe, but the expansion rate itself evolves over cosmic time. Early in the universe, expansion slowed as gravity pulled matter together. Later, dark energy caused expansion to accelerate. The Hubble constant is simply the expansion rate measured today. But if new physics affects the expansion history even slightly, the connection between early and late measurements could shift. Some theorists are now exploring models where the expansion rate evolves differently than the standard model predicts. In these models, the universe might have experienced subtle transitions in its energy content over time. Perhaps new particles briefly influenced expansion. Perhaps dark energy changed strength. Perhaps gravity itself behaves differently on enormous cosmic scales. Each possibility introduces new parameters into cosmological models. Testing those parameters requires enormous datasets, which is why the next generation of astronomical surveys will be crucial. The Vera C. Rubin Observatory, currently nearing completion in Chile, will conduct one of the most ambitious sky surveys ever attempted. Over 10 years, it will photograph the entire visible sky thousands of times. Its observations will track billions of galaxies, measure thousands of supernovae, and map the distribution of dark matter through gravitational lensing. The data will allow cosmologists to study how cosmic structure evolved over billions of years. Another mission, the Euclid Space Telescope, is already surveying distant galaxies to map the large-scale structure of the universe. Euclid's measurements will help determine how dark energy influenced cosmic expansion. Together with the Nancy Grace Roman Space Telescope, these observatories will create the most detailed map of the universe ever constructed. And somewhere in that map may lie the answer to the Hubble tension. But even if the tension eventually disappears, the investigation itself has already changed cosmology, because it has forced scientists to test their models more rigorously than ever before. Every assumption is being examined, every measurement refined, every dataset reanalyzed, and that process is revealing a universe more complex than we imagined. Because the deeper astronomers look, the more surprises they find. Galaxies forming earlier than expected, black holes growing faster than models predicted, large cosmic structures appearing sooner than theory suggested. Each discovery hints that the universe may still hold secrets beyond our current understanding. And sometimes, the most important discoveries begin with a small, stubborn discrepancy, a difference of just a few percent, a number that refuses to align with expectations. The Hubble tension may ultimately fade as better measurements arrive, or it may become the doorway to entirely new physics. Either outcome represents progress, because science advances not by clinging to certainty, but by confronting the places where our understanding breaks down. And right now, the expansion of the universe sits precisely at that frontier. There is a moment in almost every scientific mystery when the conversation changes. At first, Researchers ask whether the anomaly is real. Then they ask whether their instruments are trustworthy. Eventually, if the discrepancy survives every attempt to eliminate it, the question becomes something deeper. What is the universe trying to tell us? Cosmologists studying the Hubble tension have reached that stage because the disagreement between measurements has now survived years of scrutiny. Different telescopes, different distance indicators, different statistical methods. Each new dataset tightens the constraints, yet the gap remains, which raises an unsettling possibility. The universe may be hinting that our current model of cosmology, as successful as it is incomplete. That realization does not mean the LCDM model is wrong. It explains an enormous amount of observational evidence. The cosmic microwave background, the distribution of galaxies, the formation of large-scale cosmic structures. Few scientific models have ever matched observations as well. But models are tools, not final truths. They evolve as new data arrives, and sometimes the smallest cracks in a model reveal the path toward deeper understanding. Think again about the discovery of dark matter. In the 1930s, astronomer Fritz Zwicky noticed something strange while studying the Coma cluster. Galaxies in the cluster were moving so quickly that the cluster should have flown apart. The visible mass of the galaxies could not provide enough gravity to hold the system together. Zwicky proposed the existence of missing mass. For decades, the idea remained controversial. Some astronomers suspected observational errors. Others believed our understanding of gravity might be flawed, but over time, evidence accumulated. Galactic rotation curves revealed the same phenomenon. Gravitational lensing confirmed the presence of unseen mass. Today, dark matter is one of the central components of cosmology. It emerged from a discrepancy that refused to disappear. The discovery of dark energy followed a similar path. In the late 1990s, astronomers studying distant supernovae expected to see the expansion of the universe slowing down. Gravity should gradually pull galaxies closer together. Instead, they found the opposite. The expansion was accelerating. Something was pushing space outward. That discovery reshaped cosmology almost overnight. Dark energy became the dominant ingredient in the cosmic recipe. The Hubble tension may represent the next chapter in that story, but the outcome is not yet clear. There are still several possible explanations. One possibility remains that hidden systematic errors exist in the data. Astronomy is an incredibly challenging field. Observations involve faint signals from objects billions of light years away. Tiny calibration errors can propagate through measurements in unexpected ways. Scientists are therefore rechecking every step of the cosmic distance ladder with extraordinary care. Another possibility is that the early universe interpretation of the cosmic microwave background needs refinement. Even though the Planck Space Observatory data is extraordinarily precise, its interpretation depends on theoretical assumptions. If those assumptions change, the inferred expansion rate might shift. Then there is the possibility of entirely new physics. Perhaps dark energy behaves differently than we assume. Perhaps dark matter interacts with other particles. Perhaps unknown particles influenced the early universe. Or perhaps gravity itself works differently across the largest cosmic distances. Any of these possibilities would represent a profound shift in our understanding of the universe. But cosmologists remain cautious. Extraordinary ideas require extraordinary evidence. For now, the Hubble tension sits in a kind of scientific limbo, not yet resolved, not yet revolutionary, but impossible to ignore. Which brings us to the deeper philosophical implications of the problem. Because cosmology is unique among scientific disciplines, physicists studying atoms can run experiments repeatedly in laboratories. Biologists can observe countless organisms across generations. But cosmologists have only one universe to study. They cannot rerun the Big Bang. They cannot create a new cosmos for comparison. Instead, they must reconstruct cosmic history from the faint signals reaching Earth today. Light that has traveled billions of years. Radiation left over from the earliest moments of existence. ripples in space-time created by distant collisions of neutron stars. Every observation is a message from the past, a clue about how the universe evolved. And sometimes those clues do not fit neatly into our models. When that happens, scientists must decide whether the anomaly reflects an error in measurement or a deeper truth about reality. The Hubble tension forces cosmologists to confront exactly that choice, and the coming years will likely determine which interpretation is correct. Because new instruments are about to provide more data than ever before, the Vera C. Rubin Observatory will soon begin scanning the sky night after night. Its camera is so powerful that each image will contain millions of galaxies. The observatory will track supernova explosions across enormous cosmic distances. It will map dark matter through gravitational lensing, and it will provide new measurements of cosmic expansion with unprecedented precision. Meanwhile, the Euclid Space Telescope and the Nancy Grace Roman Space Telescope will observe billions of galaxies from space. Together, they will create a three-dimensional map of the universe, stretching across much of cosmic history. Those maps will reveal how matter clumped together over time. They will show how dark energy influenced the expansion of space, and they may reveal subtle patterns that point toward new physics. At the same time, gravitational wave detectors are becoming more sensitive. Future observatories like Einstein Telescope and Cosmic Explorer will detect thousands of neutron star collisions across the universe. Each event will provide another measurement of cosmic expansion. Within a few decades, the Hubble Constant may become one of the most precisely known numbers in cosmology. And when that happens, the tension will either disappear or become impossible to ignore. But either outcome leads to the same destination, a deeper understanding of the universe. Because every time humanity has pushed the limits of observation, the universe has revealed something unexpected. Planets orbiting distant stars, black holes colliding in deep space, galaxies forming just a few 100 million years after the Big Bang. The cosmos consistently proves more creative than our theories, and the Hubble tension might be the next hint of that creativity. A small discrepancy today, a doorway to discovery tomorrow. For a moment, step away from the equations and telescopes. Think instead about what the Hubble tension actually represents. It is not simply a disagreement between two numbers. It is a disagreement about the history of the universe. One measurement says the universe expanded at a certain pace from the beginning until today. Another says the expansion must have evolved differently somewhere along the way, somewhere between the early glow of the cosmic microwave background and the galaxies we see around us now. The universe might have changed course slightly, and if that happened, something must have caused it. The difficulty is that cosmology connects many pieces of physics together. Change one ingredient and the others respond. Adjust dark energy and the growth of galaxies changes. Alter dark matter and the cosmic web reorganizes itself. Modify gravity and the entire expansion history of the universe shifts. This is why cosmologists are cautious about proposing new physics. A single adjustment can ripple through billions of years of cosmic evolution, yet the tension continues to push researchers toward new possibilities. One intriguing line of investigation explores the idea that dark matter might interact with dark energy. In the standard LCDM model, these two components behave independently. Dark matter forms the gravitational scaffolding that holds galaxies together. Dark energy drives the accelerated expansion of space. But some theorists have proposed that these two components might communicate through subtle interactions. If dark matter slowly transfers energy to dark energy, the expansion rate of the universe could change over time. That shift might reconcile early universe and late universe measurements. Another idea involves the possibility that dark matter is not entirely stable. If dark matter particles decay slowly over billions of years, the amount of gravitational mass in the universe would gradually decrease. Less gravitational attraction could allow the expansion rate to increase slightly in the present era. Models exploring these possibilities are being tested against observations. So far, none provide a definitive solution, but the investigation continues. because the universe has a habit of surprising us. Take the discovery of exoplanets. For centuries, astronomers wondered whether other stars possess planets. Many assumed planetary systems like our own would be common. When the first exoplanets were discovered in the 1990s, they turned out to be completely unexpected. Massive gas giants orbiting extremely close to their stars, so-called hot Jupiters, nothing like the architecture of our solar system. Those discoveries forced astronomers to rethink theories of planetary formation. Today, we know that planetary systems can take many forms. Compact systems of multiple super-Earths, lonely gas giants, rogue planets drifting between stars. The universe rarely follows the simplest assumptions. Cosmology may be experiencing a similar moment. The LCDM model provides an elegant description of the universe, but elegance does not guarantee completeness. Nature sometimes contains layers of complexity that only reveal themselves when observations become precise enough. And right now, observational precision is reaching unprecedented levels. The James Webb Space Telescope is already reshaping our understanding of the early universe. Some of the galaxies it has observed appear far more massive and evolved than models predicted for such early cosmic times. These observations are still under debate, but they suggest that galaxy formation may have proceeded more rapidly than expected. If that turns out to be true, it could influence cosmological measurements derived from early universe observations. Meanwhile, surveys of large-scale cosmic structure continue to improve. Astronomers are mapping the positions and motions of millions of galaxies. These maps reveal enormous filaments and walls of galaxies stretching across hundreds of millions of light-years. Between them lie vast cosmic voids where very few galaxies exist. The entire structure resembles a three-dimensional web. Gravity shaped that web over billions of years, and the expansion of the universe determined how quickly those structures formed, which means precise measurements of cosmic structure provide another way to test cosmological models. Already, some studies suggest subtle differences between observations and predictions of the LCDM model. Nothing definitive yet, but enough to keep cosmologists paying close attention. And then there are gravitational waves. Each time two neutron stars collide, the universe provides another standard siren measurement of cosmic expansion. As detectors become more sensitive, these events will be observed across greater distances. Eventually, they may provide a completely independent measurement of the Hubble Constant, one that bypasses many of the uncertainties affecting other techniques. If that measurement confirms the higher expansion rate, the case for new physics will grow stronger. If it confirms the lower rate, the cosmic distance ladder may require revision. Either way, the mystery will move closer to resolution, and when it does, the implications will extend far beyond a single number. Because the expansion rate of the universe touches every aspect of cosmology, it influences estimates of the universe's age. It shapes predictions about galaxy formation. It determines the balance between gravity and dark energy. And ultimately, it determines the long-term fate of the cosmos. Will the universe expand forever? Will the acceleration of dark energy grow stronger over time? Or could the expansion slow, stabilize, or even reverse under certain conditions? At present, the best evidence suggests expansion will continue indefinitely. Galaxies beyond our local group will drift farther away until they disappear beyond the cosmic horizon. Trillions of years in the future, observers in our galaxy may see only a handful of nearby galaxies. The rest of the universe will lie beyond the limits of observation, but that prediction depends on the exact nature of dark energy, and the Hubble tension reminds us that our understanding of cosmic expansion may still be incomplete, which brings us to the final perspective. Because the universe is not obligated to match our expectations, it reveals its secrets gradually, through faint signals traveling across billions of light years, through tiny discrepancies in measurements, through anomalies that force scientists to ask deeper questions. The Hubble tension might eventually fade as new data arrives, or it might become the first clue pointing toward an entirely new understanding of the cosmos. Right now, we simply do not know. But that uncertainty is exactly what makes science powerful. Every unanswered question becomes an invitation to explore further. And the universe is still full of questions waiting to be asked. The expansion of space, the nature of dark matter, the mystery of dark energy, the origins of galaxies and stars. Each represents a doorway into deeper layers of cosmic reality. The Hubble Tension may be one of those doorways. A small mismatch in numbers today, a possible revolution in physics tomorrow, and somewhere in the data still arriving from telescopes, satellites, and gravitational wave detectors, the answer may already be waiting, because the universe is still speaking, and we are only beginning to understand the language it uses. If you step back far enough, the Hubble tension becomes something more than a technical disagreement in cosmology. It becomes a reminder of how fragile our understanding of the universe really is. For centuries, humans assumed the cosmos was static and eternal. Then, in the early 20th century, astronomers discovered that galaxies were rushing away from each other. The universe was expanding. That discovery alone transformed our view of existence. Suddenly, the universe had a beginning, a moment when everything was compressed into an incredibly hot and dense state. That moment became known as the Big Bang. Over time, astronomers gathered more evidence supporting this idea. The expansion of galaxies, the cosmic microwave background radiation, the abundance of light elements like hydrogen and helium, all pointed toward a universe that began roughly 13.8 billion years ago. Then came the discovery of dark matter, invisible mass shaping the rotation of galaxies and the motion of galaxy clusters. Then dark energy, the mysterious force accelerating the expansion of space itself. Each discovery added new pieces to the cosmic puzzle, and each time, the universe turned out to be more complex than scientists expected. The Hubble tension fits into this long tradition of cosmic surprises. At first glance, the difference between 67 and 73 kilometers per second per megaparsec might seem trivial, but across billions of light years and billions of years of cosmic history, that small difference becomes profound. It determines how quickly galaxies separate, how structures grow, how long the universe has existed, and how it will evolve in the future. The tension forces scientists to examine every assumption embedded in cosmology, how distances are measured, how early universe radiation is interpreted, how dark matter behaves, how dark energy influences cosmic expansion, even how gravity itself might operate across enormous distances. This process is messy and uncertain, but it is also how science progresses, because the most important discoveries often begin with tiny inconsistencies. Consider the discovery of Neptune. In the early 19th century, astronomers noticed something odd about the orbit of the planet Uranus. Its motion did not match predictions. The difference was small, but persisted. Two mathematicians, working independently, calculated that an unseen planet might be tugging on Uranus gravitationally. When astronomers pointed telescopes at the predicted location, they found Neptune almost exactly where the equations said it would be. A new planet had been discovered not through direct observation, but through the subtle influence it exerted on another world. The Hubble tension might represent a similar phenomenon, a small discrepancy revealing the presence of something unseen. But instead of a hidden planet, the explanation could involve entirely new physics, or perhaps a deeper understanding of the cosmic ingredients we already know exist. Cosmology today is entering a golden age of observation. The James Webb Space Telescope continues to peer deeper into cosmic history than any instrument before it. Future missions like the Nancy Grace Roman Space Telescope will measure billions of galaxies and thousands of supernovae. Ground-based observatories, such as the Vera C. Rubin Observatory, will create massive surveys, mapping the structure of the universe with extraordinary detail. Meanwhile, gravitational wave observatories are opening a new window on the cosmos. Each collision of neutron stars provides a new measurement of cosmic expansion. Each detection adds another piece to the puzzle. Over the next decade, Cosmologists expect the precision of expansion measurements to improve dramatically. At some point, the data will force a conclusion. Either the measurements will converge and the tension will disappear, or the discrepancy will grow too large to ignore. If that happens, the implications will be profound, because it would mean the universe is governed by physics we do not yet understand. New particles, new forces, or new behavior of space-time itself. And history suggests that such moments lead to breakthroughs. Quantum mechanics emerged from small inconsistencies in classical physics. Relativity arose from subtle discrepancies in planetary motion and electromagnetic theory. Entire revolutions in science often begin with tiny cracks in existing models. The Hubble tension may be such a crack, or it may simply be a reminder that measuring the universe is incredibly difficult. Right now, cosmologists stand at the edge of that uncertainty. They have two precise answers to the same question, both supported by careful observations, both deeply rooted in decades of research, and both refusing to agree. Somewhere between the earliest light in the universe and the galaxies surrounding us today, something may have altered the expansion of space, or perhaps the explanation lies hidden in the methods we use to measure cosmic distances. Either way, the mystery remains open, which brings us back to the most important perspective. Science does not advance because scientists are always right. It advances because scientists are willing to question their own conclusions, to examine anomaly, to test assumptions, to push observations beyond previous limits. The Hubble tension represents exactly that process. A puzzle, a challenge, an invitation to explore deeper. The universe has revealed a number that does not quite fit, and somewhere within that mismatch may lie the next breakthrough in our understanding of reality, because the cosmos has always been more surprising than we expect, and the expansion of the universe, the stretching of space across billions of light years, may still hold secrets we have only just begun to uncover. The story is not finished. In many ways, it is just beginning. There is something quietly profound about the fact that the fate of the universe may hinge on a difference of just a few numbers on a graph. Cosmology deals with the largest structures in existence. Entire galaxies. Vast clusters containing thousands of galaxies. Filaments of matter stretching hundreds of millions of light years across space. And yet the mystery now confronting astronomers is rooted in a discrepancy smaller than 10%. That tiny gap between 67 and 73 kilometers per second per megaparsec has forced scientists to re-examine nearly every assumption about how the universe evolves. But to understand why this difference matters so much, it helps to imagine the universe not as a static picture, but as a film playing across billions of years. At the beginning of that film sits the afterglow of the Big Bang, the cosmic microwave background mapped in extraordinary detail by the Planck Space Observatory. Those faint microwaves carry a record of the universe when it was only a few 100,000 years old. They reveal the density of matter, the amount of radiation, the distribution of tiny fluctuations that would eventually grow into galaxies. From that snapshot, cosmologists can simulate how the universe should evolve over time. They can run the cosmic clock forward. When they do, the universe expands, galaxies form, clusters emerge, and the cosmic web gradually takes shape. The simulations produce a universe remarkably similar to the one astronomers observe. But when the simulation reaches the present day and calculates the expansion rate, the value emerges near 67. The early universe predicts a slower expansion. Now consider the second approach. Astronomers look outward at galaxies whose light has traveled billions of years to reach us. They measure distances using stars and supernovae. They measure how fast those galaxies are moving away due to the stretching of space. Those measurements point toward a faster expansion rate, closer to 73. Both methods appear internally consistent. Both pass careful tests. Yet when compared directly, they refuse to align. At first, cosmologists try to treat the discrepancy as a statistical problem. Perhaps a subtle bias in supernova measurements skewed the results. Perhaps dust inside galaxies affected the brightness of Cepheid stars. Perhaps the cosmic microwave background interpretation depended too strongly on assumptions embedded in the LCDM model, but each of those possibilities has been examined repeatedly. Observations from the James Webb Space Telescope confirmed the Cepheid measurements with unprecedented clarity. Independent distance indicators produced similar results. Alternative analyses of cosmic microwave background data still returned values near the lower expansion rate. At some point, the conversation changed. The tension stopped looking like a measurement error. It began to resemble a genuine physical puzzle. And that realization forced cosmologists to consider something unsettling. Maybe the universe's expansion history contains a chapter we do not yet understand. To see how that could happen, imagine again the cosmic timeline. During the universe's earliest moments, radiation dominated its energy content. Photons and neutrinos filled space with tremendous energy. As the universe expanded and cooled, matter gradually took over. Gravity began pulling matter together to form galaxies and clusters. Billions of years later, dark energy emerged as the dominant influence, accelerating cosmic expansion. The LCDM model assumes this transition happened smoothly. But what if something interrupted that smooth progression? Perhaps a new particle influenced the early universe for a short time. Perhaps dark energy briefly behaved differently than it does today. Perhaps dark matter interacted with radiation in unexpected ways. Even a temporary change could alter the pattern imprinted in the cosmic microwave background, and that alteration could ripple forward across billions of years, producing the discrepancy we now observe. Cosmologists are exploring many variations of this idea. Some involve hypothetical scalar fields that briefly inject extra energy into the early universe. Others introduce new particle species that behave like radiation. Still others modify the behavior of dark energy itself. Each proposal attempts to bridge the gap between the early and late measurements, but each must also preserve the extraordinary success of the LCDM model in explaining other observations. It is a delicate balancing act. Adjust the model too much, and it breaks other predictions. Adjust it too little, and the tension remains. Meanwhile, new observational techniques continue emerging. One of the most promising involves gravitational waves. When two neutron stars collide, they create ripples in space-time detectable by observatories like the LIGO scientific collaboration. These events provide direct distance measurements, independent of the cosmic distance ladder. Astronomers call them standard sirens. The first such measurement, from a neutron-star merger in 2017, produced a broad range of possible expansion rates. But as more gravitational wave events are detected, the uncertainty will shrink. Eventually, standard sirens may provide the most reliable measurement of cosmic expansion ever achieved. And when that happens, the universe itself will decide which number is correct, or perhaps reveal something entirely unexpected, because the Hubble tension might not resolve neatly into one value or the other. It might reveal that the expansion of the universe is influenced by physics we have not yet discovered, something beyond the familiar components of matter, and dark energy. If that turns out to be true, the consequences would ripple across modern physics. Particle physics would search for new particles or interactions. Astrophysics would revise models of galaxy formation. Cosmology would rewrite the story of the universe's evolution. And perhaps most importantly, our understanding of reality would deepen once again. Moments like this are rare in science. Most research refines existing knowledge gradually, but occasionally, a small anomaly opens the door to a new conceptual framework. The ultraviolet catastrophe led to quantum mechanics. The orbit of Mercury helped confirm relativity. Galactic rotation curves revealed dark matter. The accelerating universe revealed dark energy. The Hubble tension may join that list, or it may fade as new observations arrive. Right now, scientists simply do not know. What they do know is that the universe has presented a puzzle, and puzzles are invitations. They invite curiosity, they invite exploration, they invite new ideas. Across observatories around the world and satellites orbiting Earth, astronomers continue collecting data. Each observation adds another piece to the cosmic puzzle, and somewhere among those pieces may lie the answer to why the universe appears to be expanding slightly wrong. Perhaps the explanation will confirm our current models. Perhaps it will reveal new physics hiding in the dark. Either way, the search itself is part of the adventure of science, because the universe is not just a place we inhabit, it is a story we are still learning to read, and every discrepancy, every number that refuses to fit, is another sentence waiting to be understood.